Okay, so we're recording. Time to get started. Last time we finished up section 1.6. We are doing sections a little bit out of order, right? I mentioned that before. So back to 1.1. I'm going to say very little about 1.1. Keep in mind tough choices and all that. Most of 1.1 is stuff that I think y'all either already know or can totally read on your own. So just a couple of kind of, I'm going to call them personal preferences that I thought I'd float to you. Not that it matters, but for whatever it's worth, I think this is a weird notation to use bold to indicate that something is a vector, not a scalar, because it's hard to do with a pen, right? And so it's kind of a weird choice for a textbook writing to students who are going to be using a pen. I just think that's strange. Much more convenient, I think, and natural to put the little vector hat over instead of the bold. So anyway, be aware the book is going to use bold instead of the vector hat. I'm going to use the vector hat instead of the bold. Whatever. You're allowed to do whatever you want. Okay, next. How would we represent what would seem like a reasonable way to represent this vector here? The book and others write it like this. Very reasonable at first glance. And ultimately nothing really wrong with that. But here's the other observation I'd like to make. So keep in mind that points and vectors have a natural correspondence. So in particular, P1 can, as a point, can instead be thought of as this vector. Likewise, P2 comes to us as a point, but can be thought of as that vector. And when you make that observation, it's pretty easy to realize that here's another way that you could write this green vector here, that, tail at P1, head at P2. Now, looking at the choice, then, between these two different notations, which one is better? Again, at first glance, the one on the left is a little bit more sort of obvious in its interpretation. But the one on the right has I consider to be a major advantage, and that is you can see the algebra. And why I think that matters is because algebra is useful. Algebra allows us to solve problems, right? If there is a useful piece of information encoded into what I'm talking about, I think it should be visible. That's just a personal preference. It's not important. You can see it. I mean, who cares? It's not that big a deal. But this being available, I don't see the advantage of that myself. Now, again, this is just a matter of personal preference. You can use either you like. It doesn't matter. There's plenty of precedent for the one on the left. This is just a pitch. I'm hoping to make a sale, hoping to persuade y'all you might like the one on the right. Okay, how are we doing? Is everybody on board? Questions? Feel free. That's section 1.1. Probably the fastest section we'll cover in this class, but it's a little close. There's going to be another one that's ultra fast in chapter 5. Anyway. Okay, so moving on to 1.2, a bunch of stuff about vectors that I know y'all know, but parameterizations is covered in this section, and I don't expect that y'all have seen parameterizations before. If you have, cool, but I wouldn't assume it. So here's a first cut at what a parameterization is. A parameterization gives position as a function of time. Doesn't have to be time. I like to think of the parameter as being time. Technically, a parameterization can, of course, be position as a function of any parameter. Suit yourself. Well, if you think of it as position as a function of time, then notice that's a familiar concept, right? Back in single variable calculus, you saw examples where position was a function of time, and then they talk about like the derivative, and that gives velocity. It's a pretty natural thing. I'll point out that you can think of position as a function of time as actually drawing the curve. Because literally, as you draw a curve, as you move your pen across the page, position depends on time, right? So I like to think of a parameterization that way, that it's literally drawing the curve that it's describing. Okay, so let's see an example of a parameterization. Here we go. There's, I claim that's a parameterization. Position's a function of time. You can see right here, position x comma y, and you can see that both are functions of our parameter. Again, I like to think of it as time. Okay. And we have explicit formulas for these functions. X as a function of time is cosine t, and y as a function of time is sine t. Okay, now what does this curve look like? We could, I suppose, plug in some points and then connect the dots, but we don't really know what's going on in between. We could get a rough idea, but there'd be some guesswork involved. It is a little confusing to try to keep, based on your knowledge of what the x-coordinate is doing and what your knowledge of the y-coordinate is doing, it can be kind of hard to keep track and figure out where the corresponding point is. That's a little bit hard, suboptimal in this case. Here's what I think is the better approach in this case, and that is to ask, okay, these formulas that I have for x and y, do I notice any convenient formula that relates these two things to each other? And lucky break, why yes I do. This formula right here, because after all, x and y, oh my gosh, what's happened there? Okay, my pinky finger just happened to touch exactly on that very narrow line, and it rolled me down to the very end of this section. Sorry about that. That's a first. Okay, here we go. X being something that we know, and y being something that we know. That parametric curve satisfies this equation because I know that that cosine squared plus sine squared is 1. Right? So lucky break, we just happen to notice a convenient relationship between those coordinates. Now, what does that tell us about the curve? Okay, well, keep in mind, again, what does the parametric curve do? Well, for any value of t, it gives me a location. It gives me a point. And this point, I see, satisfies this equation. This equation describes a unit circle. Connecting those dots to each other, we get that every point on this parametric curve is on the unit circle. And so, in fact, it seems like a reasonable conclusion. This is a parameterization of the circle. You buy it? Everybody happy? Okay. Sometimes you will get lucky. You just happen to notice this relationship, and you got to capitalize on freebies when they come at you. Okay, now here's another example. This one won't be quite so convenient. Let's see here. Let me zoom so we can see better. Here we go. Starting with this formula, notice we have x given to us, and we have y given to us. Right? So what is this parametric curve? What is that tracing? What is it drawing as t increases? What is this tracing? It's not immediately obvious. Do I notice any immediate freebie familiar equations that relate these two formulas? No, not really particularly. Okay. So here's what I think is a good method in this case. Notice that in this formula for x, I can solve for t. That's the first step. Solve for t in the first equation. Next, I'm going to take that t and I'm going to plug it into the second equation. Like so. Right, so again, we have these two equations. There's a formula for x, formula for y. Solve for t in the first one, plug it into the second one. And notice what pops out is a relationship between x and y, and I can simplify the algebra a little bit, and there you go. Easy, convenient relationship between x and y, and I instantly recognize this as the equation of a line, and game over. Everybody on board? Now, it's a different approach than what we did in the previous example. Why am I showing you multiple methods? The reason I'm showing you multiple methods is because there is no single method that will always work, right? So this is so my metaphor for this is tools for your toolbox. You should think of various different kinds of math problems that you're going to need to solve in this class and others as being little challenges that have to be dealt with, and you pick the right tool for the right job. It's good to have a toolbox full of tools, right? So this is a really good method for this specific example, and therefore it's a valuable tool, but it is not a good method for our previous example with the sines and cosines. Notice in particular, in order to do this example, in this first equation, I need to be able to solve for t. You can't always just solve for t. What if this expression for x, what if it was like coordinate? You can't solve for it. And this method is crash and burn. So screwdrivers are very handy tools, but they are not helpful for getting nails into boards, right? And this is that's what's going on here. Okay. All right. Now let me show you another way to solve this same question. I can fit this all on here. There we go. Let me clean up my mess. Okay, so let's see here. Another way to solve this same problem. A reminder, we have this formula for x. We have this formula here for y. Now, before we get into this next method, let me point out these two formulas, one for x, one for y, kind of have something in common, right? They look similar to each other. I feel like I could play around with this one and manipulate it and turn it into this one. And when you feel like you notice that you can manipulate one expression to turn it into the other, then here's the idea. We've got our formula for x. Here's our formula for y. Do that manipulation. Right? What do you have to do to t minus 1 to make it look like 3t plus 4? Well, I multiply by 3 and add 7. That's just playing around with algebra. And as you do that, of course, keep track of what you've done. You've got to do legal algebra. Right? But the result of doing that perfectly legal algebra is that you have a nice, easy relationship. Same exact equation that we got up there. Nice, easy relationship between x and y, and a different way to get an answer to the same question. So again, pros and cons, right? I mean, there will be situations where you don't particularly see an immediate algebraic path like that. In which case, maybe you try that, or maybe you look to get lucky, a la the first example. Pick the right tool for the right job. Okay. Pausing. Questions? Everybody's happy? Okay. Here's another example. Now this one's different. This is in space. Three-dimensional example. You can see because the points that we're tracing out they have 3 coordinates. So this is a three-dimensional parametric curve. How do we understand this three-dimensional parametric curve? I am going to point out that this looks familiar. Now, this is not exactly that our very first example with the sines and cosine, because this has a third coordinate. Right? So the fact that I see the cosine and sine there doesn't mean that I could just copy from that example. But maybe something that we saw in that initial example might be somehow useful in this case because, I mean, my God, look at that. It's just the same. The seeming part of what we're looking at is the same thing. What is the connection in between that first example and this one? So the connection, case could be made, is notice I am effectively just kind of ignoring the third coordinate. If you think about it, the process of ignoring the third coordinate, you're throwing away the z coordinate. You're just literally projecting down into the xy plane. Well, pretty literally. Right, so looking at this whole cosine and sine business, this is not telling us our curve, but it is telling us what you get when you project our curve down to the xy plane. It's, as I like to say it, this is telling us what the shadow of our curve is in the xy plane. And so knowing, as we do, that cosine comma sine is just a unit circle, what we get out of this is that this shadow down in the xy plane is the unit circle. Is that cool? All right. Okay, so now what about what's going on here? What do I do with that t thing? Well, first of all, I like that. Right? It's just t. It's a really easy formula. Pretty sure I can handle that. Whatever it means in this context, to be determined. But it's a nice, convenient little formula. So what would it mean to look only at the z-coordinate? Well, again, that's just throwing away all the horizontal information. That is a projection to the z-axis. So what I interpret from this third coordinate being just t is that this describes how the projection to the z-axis, in other words, how the altitude of this curve behaves. So altogether, I know that the projection down to the xy plane is doing this, right? Kind of going around in a circle. And I know that my altitude, as the shadow is doing this, the altitude is just kind of going up at a constant rate. And now you have to think geometrically and kind of put those pieces together and just use your geometric sense. I mean, the shadow is doing this, but it's sort of rising at a constant rate. And geometric appeal, I claim that this makes a kind of a corkscrew pattern, otherwise known as a helix. That make sense to everybody? Notice that we don't have an equation for this curve, right? I mean, in the previous cases, we ended up with equations for the curve. You don't really have equations for curves in space. An equation would give you a surface, not a curve. But nevertheless, what we do have is an understanding of the geometry of this curve that we deduce from looking at the parameterization. Okay. All right. Okay, moving along. All right. So what if we want to go the other way? So again, the last examples that we've seen, we started with a parameterization. The parameterization was given. And I then concluded information about the curve, either geometrically or algebraically, whatever. I wrote the equation of it or something. Given a parameterization, we learned about the curve. What if it goes the other way? What if you know the curve and you want to create a parameterization of it? This is called parametrizing the curve. To take a curve and find a parameterization of it. Okay. So again, tools for your toolbox. There's different methods. None of them always work. I'm going to show you several different little tricks that work in different cases, starting with my favorite, what I call the graph parameterization. The big idea here, starting with the asterisk, this only works for graphs. Not every curve is a graph. Specifically, this only works if one of the variables can be solved for as a function of the other. In other words, now when I say y equals f of x, what that means is for any given value of x, there is one and only one value of y. And furthermore, to be able to use this trick, I have to actually be able to solve for that one and only one value of y. Okay, so in that case, when you have a graph, here's the trick. It's a super easy, simple little trick. Just make sure you remember this trick. Whatever is the input variable, let that be your parameter, and you will always win. It's awesome. It's super convenient. Now again, reminder, asterisk, this only works for graphs. But in that case, let your input variable be your parameter and just watch it just fall into place. So for example, here we go. Let's start with, here's a curve. Y equals x squared. We know that curve very well, right? It's a parabola. We got the equation. We understand it geometrically. How would I create a parameterization? Okay, step one, recognize that you have a graph. as required, right? We have y equals a function of the other variable. Step 2, identify what is your input variable. Our input variable here is x. Step 3, let that be your parameter. Notice I'm literally following that instruction. I'm letting x be my parameter t. I claim we've already won. It's just a matter of letting it play out. I need position as a function of time. I already have the first coordinate of the position. I need now the second coordinate of position, so I need to know what y is. But here's the thing, if x is t, that kind of forces y to be t squared. Right? Just take x equals t, plug it into this, y is t squared. And game over, we win. We have, as required, let's see here, let me erase my mess. We have, as required, position as a function of time. Everybody good? Fantastic little method. Now, in this case, I did one where y was a function of x, and specifically it came pre-solved. Right? So this was literally just kind of putting the pieces together. Here's a slightly trickier version. Suppose, as in this example, I don't have either variable solved for. Now, your first temptation, when you see an example like this, would be to solve for y, because, you know, I don't know, alphabetical order or something, right? This is how we always did it in high school. We solve for y as a function of x. But you notice that you can't. In fact, there's no particular reason that you need to solve for y as a function of x. It's perfectly fair to view x as a function of y. That's what I'm going to do here, because not only is it not impossible, it's not even hard. Solve for x, nothing to it. There you go. So just like in our little strategy, we have one variable as a function of the other. Our input variable here is y. I let my input variable be my parameter, following the rule. Having done so, unavoidably, x must be this. And again, game over, we win. We have position as a function of time. Everybody happy? Okay. All right. Okay, nothing to it. Now let's see some harder examples. This next one is pretty geometrically challenging, but this is a good trick to know. Vector algebra can be extremely useful. So let me set up the nature of the question first, and then we'll talk about the big picture and the details. So here's our setup. We have a wheel with a axle at a particular point. It's going to be rolling along the ground. I'm going to let the x-axis be the ground. Y'all have probably seen this kind of thing before, but if for example, a bicycle has a reflector near the rim, right, of the wheel, as the bicycle rolls down the street, it'll kind of bounce around, kind of like that. Y'all have probably seen this kind of jerky motion, right, that bicycle reflectors will make at nighttime. Yeah, everybody familiar? Let's parameterize that curve. Now, this is a harder question. The first observation I will confess to is this does pass the vertical line test just fine. This is a graph. Technically, the graph parameterization is on the table, but the problem is it's really hard to solve for y. Really, I don't even know if it's possible without some major trickery. So we do not want to use the graph parameterization here. It's not convenient. Okay, what we're going to do instead is use vector algebra as follows. I'm going to recognize that a point on this curve, in other words, where the reflector is at some point in time, can be thought of more easily as the location of the axle plus if you will, sort of a spoke vector here, sort of a radius vector that I'm just going to call D. Now, why I care about that, why this is useful, we'll get to that momentarily, but just a quick observation. I mean, P is A plus D. Everybody buy it? Now let's talk about why I care about this. Why is this a good thing? This is a good thing as follows. The axle is actually super easy to understand. The axle starts here and then just goes in a straight line. Right? Nice and easy. The axle, it's always one radius of the wheel above the ground, and it makes a nice straight line. This is easy to parameterize. I'm not scared of this at all. There's some details. We'll worry about the details in a minute. But big picture, not scary. Is that satisfying? Okay. Next, let's talk about this purple vector here. What can I say about that D vector? Am I scared of that? Well, that is a little bit weird looking, and it's tempting to say that as the wheel rolls, that arrow is doing something kind of like that or something. It does look a little weird. But, very importantly, remember, I'm not actually interested in the arrow. I'm interested in the vector. Very importantly, vectors do not have locations, right? Vectors are just a direction and a magnitude. So thought of as a vector, you can write this arrow wherever you want to. It's perfectly fine and dandy. For example, let me just do like this. Here we go. I could draw that vector there. That's the exact same vector. That's the exact same vector. That's the exact same vector. Same direction, same magnitude, same vector. So the clever move is going to be to, as I have drawn down here, let's understand those spoke vectors in a very convenient way where we put the tail at the origin. Why not? Perfectly free. Much easier to see that way. Let's make our lives simpler and draw them like this. And now let's ask the question, what do those purple arrows do as the wheel rolls? As the wheel rolls, well, it just goes around in circles. And again, circles, not scary. Right? Not that bad. Well, I mean, there's some details. Again, we'll deal with the details as they come. But I feel confident that we can write down those purple vectors. So the big picture then, going back up to here, what we find ourselves looking at is a situation where the orange points that we're interested in are unapproachable directly, but indirectly, I can just say, yeah, it's blue plus purple. Blue is easy. Purple's easy. Adding is easy. Right? And so that's going to be our foot in the door. Vector algebra. Turning a hard problem into the sum of two way simpler problems. Okay, now the details. Let's talk about the axle. Here's a picture of the axle. Right, again, it just goes in a straight line like this. Pretty easy to notice. And I just need to get this all on the page here. Pretty easy to notice that the y-coordinate will always be A, the radius of this wheel, because, I mean, it's the axle. It's the whole point is that it's the thing that's not moving. Vertically, that is, not moving. So the y-coordinate is just A. Nothing to it. A little bit of a trickier question is to ask, how do I find, again, here's our axle, how do I find the x-coordinate here? That's going to require a tricky observation that I did not think of on my own. Somebody showed me, right? Now I'm showing you, so you don't have to think of this on your own either, but it is a tricky observation. I'm impressed with whoever first noticed this. And that is, the x-coordinate is the same as this distance. That distance is the amount of road that has touched rubber. If you think about it, with the wheel starting here, this is where the rubber was first touching the road, and as the wheel rolled, now here's where the rubber's touching the road. This is literally the amount of road that has touched rubber. And the tricky observation is that the amount of road that has touched rubber is equal to the amount of rubber that has touched road. And I'm going to let you sit on that and think about that for a couple of minutes. This is just a physical appeal, right? Purely physical appeal. But when you roll a wheel, right, just imagine rolling, as you roll just a little bit of it, in some sense the rubber is kind of following the road. Sort of there's no slipping, right? So that's, again, just physical intuition, but I expect that the x-coordinate here, namely this distance here, is the same as that purple distance there. Okay, something to digest. Okay, so who cares? Why is this a win? This is a win because that purple distance is actually pretty easy to compute. At least it's pretty easy to compute in terms of this angle, t. Talk more about t in a moment. But calling as I will this angle here t, we're looking at the arc length of a circle where I know the radius and I know the central angle, and this is an easy formula from high school geometry, and that is that arc length is radius times angle. So I hope you all remember that one. Boom. So when we now have position of our axle as a function of t as a function of this angle right there. Now, before we celebrate and go on to the next one, let's talk about t. Where did this angle t come from? I'm choosing it because it's convenient. If you think about as this wheel rolls, how would I sort of keep track of where how much the wheel has rolled? And you have various choices. I just make the observation that at the start, that angle t is 0, and then as the wheel rolls, t is increasing. So it seems like a pretty reasonable choice. It's something that starts at 0 and then increases as the time passes. I might as well think of this as representing time. Notice, by the way, I've never said how fast this wheel is rolling, right? How fast the wheel is rolling doesn't even matter. All I'm interested in is the shape of the curve, not how fast we draw the curve. So I'm perfectly within my rights to just say, yeah, I'm going to let that angle be t. Is that cool? Okay. All right. Okay, moving along. Let's talk about this d vector now. And let's see here. Reminder, we've already decided that angle there is our t. That's our parameter. How are we going to understand this purple vector? Here's the thing. T is actually not particularly convenient for that. Let's set aside t for a second. How would I wish that I could represent this purple vector? I would like to represent it in terms of this angle theta. And the reason why I would like to represent it in terms of that angle theta is because this is how high school trig works, right? This is how sine and cosine are defined in the first place, is by measuring this angle called theta as measured from the positive part of the x-axis and understood to be increasing as you go counterclockwise. That's just what theta is. Sine and cosine are super easy in that sense. And from this point of view, this purple vector, well, that's kind of hard to see at this point, isn't it? This purple vector as a function of that blue angle theta is really easy to write down. This is basically straight out of the definition of cosine and sine. Okay. So I kind of have a formula for d, but it's in terms of theta instead of t, and I need it in terms of t. So the clever move to make then is to look at your theta that you have in the picture, look at your t from the previous picture. Notice that as the wheel rotates, t increases as theta decreases. They're always kind of complementary to each other in the sense that they always add up to 3/4 of a turn. Namely, they always add up to 3 pi over 2. When t equals 0, theta is 3 pi over 2, etc. Right, oh, yeah, question. Yeah.
Isn't t moving in the other direction, so wouldn't you be adding the t?
Well, I hear you. So it is a little bit weird to think about, angles as, having directions. But this angle t is defined as 0 here and increasing as you go clockwise. Right? So it's kind of, you have to just keep that in mind, right? Theta is defined as 0 over here and increasing as you go counterclockwise. And so I'm just going to make the geometric appeal that they add up like this. Is that satisfying? Okay, cool. Anybody else? Everybody's happy? Okay. All right. So if they add up to 3 pi over 2, I can just straight up solve for theta. Right? Here's my formula for theta. Theta is that. And I can take that formula for theta and pop it into there, and that'll give me, cosine and sine of a sum of two angles. Y'all may recall the angle addition formulas from way back when, right? High school trig. And most high school trig classes apparently let you get away with not memorizing those formulas. They're going to actually be really useful in Math219. And for those of you who are engineers, they're going to be useful for a lot more than that. Likewise, physics, probably some other majors. But anyway, for the purposes of Math219, it's going to be very useful, and I need you to know those formulas. So heads up, you are expected and assumed that you will memorize those formulas for the angle addition for sine and cosine. So make sure to know those. And once you know those, then this expression here turns into that formula right there. And that's a good exercise to do on your own, just to make sure that when you plug in this formula for theta, apply the angle addition formulas, you get that for your d. Okay. And it's all over but the shouting at this point. So let's celebrate. Keep in mind our original setup was that our thing that we're trying to understand is the axle, which I solved for here, plus this d vector, this purple thing here, right? The d vector that I solved for there. And then final answer, the thing that we're trying to parameterize, this wacky curve there, is parameterized by literally this sum as per our original term. All in terms of t, yeah.
Sorry, can you quickly go over how you got that d vector with the a cosine theta, a sine?
Yeah, so that's just I'm making a reference to the definitions of sine and cosine. If you look at the definition of sine and cosine, a lot of people do it in terms of triangles. That's maybe an okay sort of like very, very initial sort of definition. But the problem with triangles is you cannot have a triangle that has an angle that's like 17 pi, right? And so that the triangle point of view on sine and cosine just doesn't really work very well beyond very limited circumstances. So the actual definition then of sine and cosine is that you look at the unit circle, you define the angle theta as written here, counterclockwise, 0 here, etc. And sine and cosine are literally defined as the x and y coordinates of the corresponding point on the unit circle. And so taking that as the definition, easily confirmed to be equivalent to the triangle definition, this is sort of an immediate consequence of that. Yeah. Is that satisfying?
Yes.
Okay. Cool. Okay, so vector addition, right? Turn hard problems into sums of much, much simpler problems, and really valuable method. Okay, how do you parameterize a line? There's various different ways to do this. Again, I'm going to presume that the line that we're interested in, that we know a couple of specific things. Let's suppose that we know a point on the line and that we know a vector parallel to the line. Take that as a given. Now, how would I use this to create a parameterization? Well, just keep in mind, I just need to trace the line. I need to come up with some formula that as t increases, I literally draw out the line. And check it out. If you start on the line and then move parallel to the line. Now, wait a second here. V was given to be parallel to the line. Notice that means that any scalar multiple of V also parallel to the line. Right? So what we've got in this formula here is that we're starting on the line and then we're moving parallel to the line. That means that we are staying on the line. So this formula right here, this formula gives you a point X that literally traces out that line as desired. Everybody happy? Now this is just a pat, just make sure to remember this one little trick, right? Always, if you want to parameterize a line from a point in a parallel vector, then just remember that one trick. This is what works very conveniently. Okay. All right. Okay, here's another example. Sometimes the thing you want to parameterize is not that different from something you already know how to parameterize. Sometimes you can take an existing parameterization, just tweak it just a little bit, and get the parameterization that you need. So here's the circumstance I want to entertain. Let's suppose we want to parameterize this ellipse. Right? So high school algebra, hope you all remember all of that business. And we have an ellipse there that's sort of, semi-radius. Well, let's see, what do you call it? I forget the word. Anyway, the radius in the x direction, the semi-major axis, I guess they call it, is 3, and in the y direction is 2 per the formula. Okay, do we know how to parameterize this? Not immediately, but we do know how to parameterize the unit circle. And there it is, unit circle. That was our very first example. So I claim that this circle and that this ellipse are not that different from each other. And I'm going to make a reference to another fact from high school algebra. Hope you all remember this one. If not, then here's a cool fact about ellipses. Ellipses are what you get when you take the unit circle and you stretch appropriately in the x direction and then stretch appropriately in the y direction. Ellipses are just stretched out circles. That's it. So, okay, cool. So what's the tweak I need to do then? How am I going to have to adjust this purple curve to turn it into the orange curve? Well, apparently I need to stretch by a factor of 3 in the x direction. And how am I going to do that in the parameterization? Keep in mind, I already know the cosine and sine parameterizes that purple curve. What would it look like algebraically if I want to stretch by a factor of 3 in the x direction? I'm just going to multiply all of the x coordinates by 3, which is easy to do. Does that make sense? Okay. And then likewise, now apparently I'm going to have to stretch vertically. It would seem from the numbers here that I'll be stretching by a factor of 2 in the y direction. And again, okay, easy to do. How do I stretch by a factor of 2 in the y direction? I'm going to literally multiply all the y coordinates by 2. So I have now stretched out the circle to make this ellipse. And notice, starting from a given parameterization I already knew, cosine t sine t, I tweaked as appropriate to make this not that different, slightly tweaked curve E. Everybody good? Okay, last little quickie exercise for y'all to do at your leisure. If you take this parameterization that we've come up with, if you plug it into that equation for the ellipse, just confirm that, yep, sure enough, it satisfies that equation. It works. Okay. All right. Okay. Moving along. last thing we're going to talk about is a sort of a comparison between parameterizations and equations. Parameterizations and equations do have something important in common. Both parameterizations and equations are algebra that you write down to help you understand a curve. Right? So they kind of feel kind of like the same thing. They're algebra that represents a curve. So what's the difference? Right? Well, the difference is in how they represent a curve. And that difference is extremely important. It's very important to keep in mind what that difference is. Parameterizations help you understand a curve by literally generating points that are on the curve. You give me a value of t, I plug it into the parameterization, out comes literally a point on the curve. So I like to think of a parameterization as being a point generator. Is this what equations do? Absolutely not. An equation doesn't generate anything. An equation is what I like to call a point tester. So specifically, if you have an equation, what you have is a way to test candidates that may or may not be on your curve. So if you've got an equation and someone says, hey, here's a point. Is this point on that curve? What you do is you take that point, you plug it into the equation, and out comes either that the equation worked, in which case, yes, that point is on the curve, or out comes it failed, no, it did not work in the equation, and therefore, no, that point is not on the curve. It's literally testing points. It's not generating anything. Does everybody see the distinction? Right? There's an important distinction. And again, yes, they are both algebra, and yes, they both help us understand curves, but in these very, very different ways. Okay. By the way, for whatever it's worth, I have a personal, pet peeve, I guess is the term. Some people like to call parameterizations parametric equations, and it just totally bugs me because the whole point to having a word is to distinguish it from what it's different from. So that the idea that they would use the word equation while they're trying to distinguish it from an equation, I think is just silly. Don't care for that at all. That said, it's a very common term. Heads up, be aware of the term. When you see the term parametric equations, I encourage you to kind of roll your eyes and then say, okay, they meant parameterization. Okay, so here's how we can use this understanding. Let's answer this little problem here. I have a parametric curve in 3 space, and I want to know where does that curve intersect this plane for which I have an equation. Okay, so the way we're going to do this is we're going to make sure that we first understand what we have, and then we're going to figure out how to make the pieces fit together. I have a point generator, and I have a point tester. I'm looking for a point that is on both. Right? I'm looking for a point that's on the curve and also on the plane. And the way I'm going to find said points is I'm going to generate points, and having generated points, I'm then going to test to see which of those points worked. Right? So explicit formula right here for the parameterizations, copying from up here. This literally generates points that are on my curve. Of these points, I would like to know under what circumstances are they on my plane. Again, my plane has this equation, so you plug in to that equation, and then you just solve for t and see what values of t actually give you the satisfactory points. Okay, so now real quick, all together, what this does, given a value of t, that t will generate points that satisfy the equation of the plane if and only if this happens. So what we want to do is solve this equation. When you solve that equation, what you have now, these are the values of t that generate the right points. Do just make sure to remember that the question was asking for the points themselves. The points themselves are these, and so t equals plus or minus 1 doesn't really quite cut it. That's you're almost there, right? But to get the points, you have to plug into the parameterization and see what comes out of the parameterization there. Okay, everybody happy with that? Okay. All right, this is a pretty good place to draw the line. We will pick up here on Wednesday. Don't forget we have a long weekend. See y'all on Wednesday. Have a good one.
Have a good long weekend.
Thank you. Thank you.